Today, we will be discussing a beautiful phenomenon of aquatic life, the pistol shrimp. The pistol shrimp is a family of crustaceans that lives in the Pacific, Indian or Atlantic Oceans. With 19 unique species, the pistol shrimp is defined by its disproportionately large claw, which grows as large as half of its body. This claw can grow from either side of the body, and the pistol shrimp even possesses the ability to reverse the claws. For example, when the snapping claw is lost, the missing limb will regenerate into a smaller claw, and the original, smaller appendage will grow into a new snapping claw. The larger claw itself consists of two parts, a moving hammer and a stationary equivalent of a striker. The hammer can be cocked back to a 90-degree angle and released, snapping the hammer back to the striker. As the name implies, the pistol shrimp is one of nature's biggest gangsters, and in fact keeps that thang on him. Repping the equivalent of an underwater blicky, the pistol shrimp uses its claw to generate a cavitating high-speed water jet for hunting prey. Cavitation is the rapid formation and collapse of vapor bubbles within a liquid. This occurs when the static pressure of a liquid becomes smaller than its vapor pressure. This can be most easily understood in terms of potential and kinetic energy. Because energy is neither created nor destroyed, a change in either form of energy must be compensated for by changing the other form. In the case of the pistol shrimp, the claws increase the kinetic energy of water by shooting water at high velocity. Consequentially, the water loses potential energy or pressure, and this pressure falls below the water's vapor pressure, creating water vapor. The collapse of the bubble produces temperatures equivalent to the surface of the sun and even creates light, a phenomenon known as shrimpoluminescence. To explain how this process occurs, Sheldon J. Plankton will explain adiabatic processes.
Because the collapse of the bubble occurs quickly, it is semi-reasonable to assume that little heat transfer occurs. So, if there is approximately zero exchange in heat with the surrounding, the internal energy of a system will increase by -P times dV. We can relate energy to temperature because the change in internal energy is also equated to the moles of gas multiplied by the heat capacity of the gas times dT. Under ideal circumstances, we can see the derivation of the following equation gives the final form T. 2 divided by T, 1 equals V, 1 over V2, raised to the 1 over C. However, the case of the pistol shrimp is an irreversible process. So the derivation of the equation results in T, 2 equals T1 minus the quotient of external pressure times the change in volume over the number of moles multiplied by the heat capacity. For shrimpoluminescence to occur, the temperature of the bubble compression must reach a temperature of at least 5,000 Kelvin. However, it is not the temperature that causes cavitation damage, it is the shock wave that results from the bubbles collapsing. As the bubbles collapse, the local liquid reaches high velocity, putting high pressure on other nearby objects. In the case of the pistol shrimp, prey are hit by these liquid jets, causing damage and even killing them. Now, if you would excuse me, I think a pistol shrimp is swimming towards me.
Thank you for that explanation, Plankton. It is amazing how these animals have evolved to manipulate physics to aid in their survival. Thinking about how simple aberrations in DNA can eventually lead to the geometry of the pistol shrimp's claw really puts into perspective the creative capacity of nature and the scope of physics. Here is a feature of Morgan Freeman, just for the hell of it.
Hello everyone, I am Morgan Freeman, and I hope you enjoyed this video of the physics behind the pistol shrimp. Thank you for watching, and have yourself a Merry Christmas.